Hello class, this is CSE-5720, Section 2, Week 5, Fall 2025. Alright, so, in the last video, we began our intro to SQL, a little bit of the history of SQL, and looking into how to perform a few basic queries in SQL as well. Now, keep in mind that Chapter 3 is big. So much so that there's a part 2. Okay. Let's recap everything that we've talked about so far from part 1. We looked at the data types supported by SQL. We looked at the various constraints that SQL has. We talked about schema and attribute definition, and we talked about queries and how queries are performed or not performed. So we covered so far sections 3.1 to 3.4. Now we're looking at 3.5. We're going to start this off with set operations. So this is going to be a review on set theory. You are probably familiar with the three main operations in set theory: union, intersect, and set difference, or except. So the union of A and B, that's A union B. Basically, you're talking about the collection of objects, the collection of things that would fall under either set A or B. Intersect is the collection of things that fall under sets A and B. And the set difference, A minus B, or also denoted as A backslash B, those are the things that are contained in A but not B. And they all correspond to three keywords in SQL: union, intersect, and except. For this section, we are gonna have the following running example. We have the section relation. So these are all the class sections in our university example. So C1 is the set of all classes taught in fall 2009, which we can obtain using this query. So I said we were gonna use this section table. Rather, we're gonna use the result of applying this query. So we can just apply this query right here, and now we have the set of all classes taught in fall 2009. The second set, C2, we also get it from this. We also use this table as input, but we apply this query. This is the set of courses taught in spring 2010. There we go. So now we have C1 and C2. Union is basically, if we perform the union between these two sets, we get a new set that contains everything from both sets. Union does not preserve duplicates. So C1 union C2, we can write it as the union of those two separate queries. And now we have C1 union C2. All the courses offered within the 2009-2010 academic year. If we want to retain duplicates, we say union all instead of union. Intersect is, it produces a relation that contains whatever entries appear in both C1 and C2. So if we perform this query, C1 intersect C2, there's one thing in common between C1 and C2. So C1 intersect C2, that tells us that CS101 is offered in both fall and spring. Except it's also known as minus in some implementations. So what this does is, well, we can perform C1 except C2 by performing this query. And what this does is, we find the tuples that appear in the first relation that don't appear in the second relation. So what appears in C1 that does not appear in C2? So CS-101 appears in both C1 and C2, but C1 only has, let me go back. CS-347 and Physics 101, those appear in C1, but not C2. So these are just classes that are offered exclusively in the fall. Also, except is not commutative, order matters. So if we did C2 except C1, it's going to be different from C1 except C2. So we can just modify our query, so we get C2 except C1. If we did that, then we get the classes that are offered exclusively in spring. So C1 except C2, these are classes exclusively offered in the fall. C2 except C1, these are classes that are offered exclusively in the spring. Let's talk about null values. They bring up challenges when it comes to relational operations. For example, what's 2 plus null? Or what does 1 is less than null evaluate to? Let's look at arithmetic first. That's a little bit easier to do. If we add, subtract, multiply, or divide, and one of the operands is null, the outcome is also null. And that's because null represents an unknown value, so if we add, subtract, multiply, or divide null with anything, we have an unknown value that we're going to do stuff to that results in an unknown value also. So 2 plus 2 equals null. Comparisons are more problematic. What does null 1 is less than null equal to? It's incorrect to say that this expression evaluates to true because we don't know what null is supposed to represent. But by the same logic, it's also incorrect to say that this expression evaluates to false. So we have it evaluate to a third value, unknown. Because we don't know whether null, this unknown value, is supposed to be less than or greater. We don't know whether this unknown value is greater than or less than 1. And because we don't know that, we have it evaluate to unknown. So we have to extend our Boolean operations of and, or, and not to handle the value unknown. So if your operands are true and unknown, A and B are unknown, and A or B is true. If your operands are false and unknown, A and B is unknown, and A or B is also unknown. And if you have operands unknown and unknown, A and B is unknown, and A or B is also unknown. With the unary operation of not, if your operand is unknown, not A is also unknown. If the predicate of a where clause evaluates to either true if the predicate of a where clause evaluates to either false or unknown, then the tuple is not added to our result. Remember that where clause that basically added rows to an output table that satisfy a condition? Well, if you apply that predicate to a row and we get the result of false, then that row is not added to the table. But if we apply that same predicate to another row and we got the value, the output of unknown, then we don't add that to the table either. There are operations that work directly with null values. The isNull predicate tests for a null value. We can combine this with not to get isNotNull. So, is this value null or is this value not null? Some SQL implementations add the isUnknown clause, which checks whether the result of a computation is unknown, which we can also combine with not to get the isNotUnknown operation. So we can have a query, for example, select name from instructor, where salary is not null. So we are looking for instructors whose salaries is known. Let's look at aggregate functions. So aggregate functions take a set of values, or a multi-set of values, as input and output. No, let me go back. Aggregate functions take a set of values as input and it outputs a single value. What's an aggregate function? Well, they're pretty simple to understand. If you take the average of a set of values, that is an aggregate function. Finding the minimum of a set of values, that's also an aggregate function. Same is true for maximum, total, and count. What's the total of these values? Well, basically we are going to add everything together from that set. We get the total. That is an aggregate function. How many values are in the set? We can just count up all the values. That is an aggregate function called count. So these 5 operations are all aggregate functions. Let's try it out. Suppose we want to find the average salary of all computer science instructors. We can do that by performing this query. Select average salary from instructor where department name equals computer science. Let's evaluate this query step by step using that sequence of steps that we talked about in part 1. First, we evaluate the from clause, but there's only one relation, so let's just skip over to the where clause. So, we want to apply the where clause where department name equals computer science. So we want to get all the rows where the department name attribute is computer science. There we go. Now that we have this table, we can now apply the select clause, select the attribute salary, and then find the average of that. So what's the average of 65,000, 75,000, and 92,000? That's 73,333. If you have a query like this, it might also be worth renaming the attribute salary to something like average salary. So we can just alias that. So select average salary as average salary. The min and max functions work exactly as you would expect them, such as find the salary of the lowest or highest paid instructor in such and such department. When finding the average, you must keep duplicates. Otherwise, the average won't be properly calculated. This is already the default behavior of average, however, but a more complex query might inadvertently remove duplicates. Though there are cases where you do want to remove duplicates, like how many unique instructors have taught during Spring 2010. To remove duplicates, we use the distinct keyword before the attribute. So select count distinct ID from teachers where semester and year is Spring 2010. So, what is it saying? It's basically find all the unique teachers who taught during Spring 2010. And we're finding them based on their instructor ID. Because that's the only information in this table. So the teachers relation is a table that says which teacher is teaching which classes. And these are teaching assignments for fall 2009, spring 2010, and summer 2009. If we want to find all the unique teachers who taught during spring 2010, well, this is the query that we would use. Here they all are. Next is to remove the duplicates. There we go. Oftentimes, count is used to count the number of tuples in a relation. Additionally, the distinct keyword does not work with count star. The distinct keyword does work with max and min, even though it doesn't change the result. If duplicates are desired, replace distinct with all. However, the default for count is to include duplicates, so adding all is redundant. So select count star from instructor. yeah, you can't use the, so you could, anyway. I guess this is something that we have to practice in the labs, by the way. So, I guess your next lab is going to, it looks like your next lab is going to be some of these more advanced operations, even though we're not in chapter 4 just yet. Sometimes we would like to use an aggregate function on not just one set of tuples, but rather groups of sets of tuples. So we group by. We use the group by clause, where we group tuples by attributes. Group by attribute. So let's try this example. Consider the following query, which finds the average salary for each department. So now, we're not finding the average salary for everyone, we're finding the average salary for each department. Since there's only one relation, let's start by grouping all tuples by department. So here's our query. Select department name, average salary as average salary, from instructor, group by department name. So now we are going to sort this table by department. There we go. Then, we select the attributes department name and salary. And then, for each group, we find their average. So now, we have an average salary of each department. Find the average salary of each department. Sometimes it's useful to state a condition that applies to groups rather than tuples. So we do this using the having clause. So let's consider the following query. Find the average salary for departments whose average salary is greater than 42,000. Select department name, average salary as average salary from instructor, group by department name, having average salary greater than 42,000. Let's try it out. First, we group all rows by department name. Then, we select the department and salary attributes. And now, we can find the average of each grouping. And then, we only consider the departments whose average salary is greater than 42,000. And here's the result of that. Find the average salary of instructors in departments whose average salary is more than $42,000. Hey, remember that sequence of steps on how a query is processed? Let's add the having and group by clauses to that sequence of steps. Here it is. Join the relation specified in the from clause. If present, apply the predicates specified in the where clause. If present, group tuples based on the group by clause. If present, groups that do not satisfy the having clause are removed. And then output the attribute specified in the select clause. And if you are performing a Cartesian join, only produce tuples that satisfy the where clause. You want to see a tuple? You want to see a query that has all 5 things? There you go. Try to figure out what this one does. Select course ID, semester, year, section ID, average total credit from X natural join student where year equals 2009. Group by course ID, semester, year, section ID, having count ID greater than or equal to 2. See what this does. So now we get to aggregation with nulls and bools. Null values also complicate the process of aggregate operations. For example, what if we want to find the average of a set of values, and one of those values is null? What if we wanted to sum up every instructor's salary, and one of those salaries is null? What happens now? For SQL standards, all aggregate functions, except for count, ignore null values. So if we perform this query, select sum salary from instructor, we ignore null values. Due to the potential presence of null values, if the aggregate functions are applied on a relation that is empty, count returns 0 and all other aggregate functions return null. Finally, there are 2 aggregate functions that work on a collection of Boolean values, sum and every. Sum returns true if at least one bool in the collection is true. In some implementations, it's called any. All returns true if every bool in the collection is true. Both sum and all also work with comparison operators. What does this mean? Well, have you ever had to do an operation where you had to make sure you had a set of bools and they were all true? That's what all is for. All collection of bools returns true if every bool in the collection is true. Sum returns true if at least one bool in the collection is true. So this already sounds like a and an OR gate. But the inputs for those gates are going to be Boolean values from one entire column in a table. Now we're getting spicy here. Nested queries. We can nest queries. A select from where expression can be used as a subquery for another query. And then that can be part of the where clause or the from clause. So let's consider the former, where we have a select from where expression as part of the where clause. Oh, by the way, a little bit of a life hack. If you ever see former or latter in a sentence, former means the first. F is for first, F is for former. Latter talks about the thing that comes later. The word latter looks like later. There you go. So, select attributes from relations were attributes in select from where. Select attributes from select from where were predicate. We're only going to consider this case first. The first use is to test for set membership. The in keyword is used to test for membership, and not in is to test for the absence of membership. Let's bring back C1 and C2. We used these earlier to demonstrate the set operations union, intersect, and accept, but we can rewrite them as nested queries. So here's the queries for C1 and C2. Rather, the queries that produced C1 and C2. Remember, the output of a query is another table. So tables go in, one table comes out. We can rewrite these as a query that doesn't use union, intersect, or accept, but we can use nested queries for these. So let's try it out. So here are the queries for producing C1 and C2. Let's revisit the intersect query and rewrite it. Remember that this query searches for all courses that are taught in Fall 2009 and Spring 2010. So remember, we used C1 and C2 as our running examples for producing different sets that represented different class offerings, like classes that were offered exclusively in the spring, or classes that were offered in both fall and spring. Those queries that involved C1 and C2, those were the questions that those queries were answering. So, this query is looking for courses that are taught in both fall 2009 and spring 2010. We can write it as the intersection of two sets, but there's another way to write it. Let's go through that step by step. First, let's copy the query for C2 and use that as part of our subquery. Now we can consider the rest of the query. We want all classes that are taught in fall 2009 that are also taught in spring 2010. Let's copy C1 since most of that wording is there. And all that's left to do is to join the two queries into one by using the in keyword and adding course ID in C2. So, select course ID from section where semester year equals fall 2009 and course ID in select course ID from section where semester year equals spring 2010. Let's rearrange it to get this query where we are finding all classes that are taught in spring 2010 and fall 2009. The fact that there's more than one way to achieve the same result is actually a good thing, because it lets users think about how to arrive at a solution that feels most natural to them. Like how in a video game, in a video game you have video game challenges, but there may be more than one way to surmount the same challenge. Different players could have different strategies that surmounts the same challenge. To that end, let's also rewrite another query. So, all classes taught in fall 2009, but not spring 2010. So here it is as the difference of two sets, and here it is as a nested query. Finally, set membership works on an arbitrary relation. Instead of testing for one attribute, we can also test for multiple attributes. This query says, find all unique students who have taken courses taught by the instructor whose ID is 10101. Select count distinct ID from takes, where course ID, section ID, semester year in. Select course ID, section ID, semester year from teachers, where teachers taught ID equals 10101. Let's rewrite another query. This was one of the queries from the previous set of slides. Find the names of all instructors whose salary is greater than at least one biology instructor. Select distinct T dot name from instructor as T, instructor as S, where T dot salary is greater than S dot salary and S dot department name equals biology. Let's split it into two queries. Find the names of all instructors. Let's put that on the left. We're gonna leave the where clause blank for now. And then find the salaries of biology instructors on the right. Select salary from instructor where department name equals biology. This is our subquery, and we're going to eventually combine this with this. The full query should be, find the names of all instructors whose salary is greater than at least one biology instructor. And SQL represents that phrase, greater than at least one, as greater than some. We can combine that plus our subquery here to fill in the blank. So all we gotta do is where greater than some subquery, and we just put this as our subquery here. So now we have this query. So the difference between this and this is we don't need to alias the same table under two different names. The keyword sum can be paired with every comparison operator. So we can have less than sum, less than or equal to sum. This is S-O-M-E sum, not S-U-M sum, by the way. So, less than sum, less than or equal to sum, greater than or equal to sum, greater than sum, equal to sum, and not equal to sum. Early SQL implementations used any instead, and newer implementations support any and some, which are synonymous to one another. Oh, and the same is true for the keyword all. Greater than all, less than all, equal to all, or not equal to all. Let's look at greater than or equal to all as part of the following query. Find the departments that have the highest average salary. In addition to greater than equal to all as part of our subquery, this requires grouping, having by, and average as part of our query. So let's start with find the average salary of each department as a subquery. Now we can write the rest of our query. All information is in the instructor relation, so we can fill in the select and from clause as select department name from instructor. Since it's average salaries by department, we group by department and add having average salary. So group by department name, having average salary. Finally, we want the departments with the highest average salary, so we add greater than or equal to all, followed by our subquery. So, having average salary greater than or equal to all, subquery. And this is our final query here. Hey, remember that query with the biology instructor? What happens if we replace the keyword sum with all? What what is this query asking? The previous query asked to find instructors whose salary is greater than that of at least one biology instructor. So by replacing the keyword some with all, it's finding instructors whose salary is greater than every biology instructor. But since our data instance only had one biology instructor, if you go back a couple slides, you'll see our list of instructors and it only had one biology instructor. These two queries produce the same result. It would not if we hired a second biology instructor. Unless they both had the same salaries. Then we'd have to hire a third biology instructor and give them a different salary, just to prove that these two queries produce different results. Testing for empty relations. SQL can determine if a subquery returns any tuples by using exists, where it evaluates the true if the subquery has tuples. Not exists evaluates the true if the subquery results in an empty table. Earlier, we had the query find all classes taught in fall 2009 and spring 2010 in two different ways. So, yeah, we saw two different ways to write the same query. One using one as the intersection of two sets, and another way using a nested query. There is another way using exists. Let's take this nested query and split it into two. Now, let's use the exists keyword, so let's start there. Since we're testing whether tuples in the outer query, that's the upper left query here, are within the subquery down here, we're testing whether tuples here exist in here. So we must select everything within the subquery, so we replace course ID with star. We also need to add a few more attributes from this. Because the two queries are using the same relation, it's necessary to alias the two so we can differentiate between the two. So, select such and such from section SS. This is our outer query, and then our subquery, select such and such from selection ST, where semester year equals spring 2010. Finally, we can use the alias query S as part of our subquery. This lets us match course IDs. Using an alias relation in this way is called a correlated subquery. Also, the distinct keyword is redundant, so we can remove it. So this is the final query. The outer query tests for whether tuples for fall 2009 exist in the subquery for spring 2010, and with course IDs that match the outer query. All these queries, all three of these, produce the same result. Pick your poison. SQL can also check whether a subquery has duplicates in its result. This is done by using unique, which returns true if the subquery has no unique tuples, though not all implementations of SQL may support this. So let's consider the query, find all 2009 courses that were offered at most once. If a course isn't offered in 2009, then the subquery returns an empty result and unique evaluates the true. Select t.courseid from course st, where unique, select r.courseid from section sr, where t.courseid equals r.courseid and year equals 2009. Find all courses taught in 2009 that were offered at most once. Of course, we can do the opposite using not unique. So, we can take our previous query and change the wording, and now we are finding all courses that were taught in 2009 that were offered more than once. And all of that is discussions on how to put a subquery in the where clause. What about the from clause? The main idea is this. A select from where expression produces a relation, which can then serve as a relation for another select from where expression. So the output of a query is another relation, another table. We can use that as the relation in our from clause as well. Earlier, we saw a query that asked for the following. Find the average salaries from departments whose average salary was greater than $42,000. We can rewrite that using a nested query. We don't need to use the having clause. When we use the having clause, we write it like this. Select department name, average salary as average salary from instructor, grouped by department name, having average salary greater than $42,000. This is using the having clause. If we write it as a nested query, we can rewrite it as follows. Select department name, average salary. From select department name, average salary as average salary from instructor, grouped by department name, where average salary is greater than $42,000. You see what's going on here? We are evaluating a query and using the result of that to evaluate another query. It's queries all the way down. And it might be a better way to think about this query. First, let's evaluate the subquery. Find the average salary of each department, which is what is being asked for here. Select department name, average salary from instructor, group by department name. Group tuples by department name, then find the average of each group. Then select the appropriate attributes, department name, and salary. And now we have the result of our subquery, which then we can use as part of our next query. So our query is select department name, average salary from subquery, where average salary is greater than $42,000. There's only one department whose average salary is lower than that. That's the music department. So that is our final output. Now we have all the average salaries from all departments whose average salary is greater than $42,000. Basically, we performed a query and used the result of that to perform another query. This might be easier to think about than the alternative. Most SQL implementations allow nested queries within the from clause. It's also possible to alias the resulting relation, although this isn't supported by all implementations. So, as a nested query or as an alias nested query. So far, all our queries had up to 3 clauses, and in some cases, up to 2 more additional clauses, group by and having. There's another clause that we can also add, with. So here's our select from where, select attributes from relations where predicate, with temp relation as select from where, select attributes from relations where predicate. The with clause, WITH with. The with clause defines a temporary relation whose definition only exists within the query in which the clause occurs. Not all implementations support with, by the way. So let's consider the following example. It defines a temporary relation max budget with the max budget value as subquery. Select max the budget from department, select budget from department, and max budget, where department.budget equals max budget.value. The relation max budget is produced by finding the largest budget. Select max budget from department. Which department has the largest budget? It's the finance department, of course. Oddly appropriate, though. So now we can use that information to create a new temporary relation, a 1-column, 1-row table, and the only value in it is 120,000. That is the largest budget that we got from our previous query. We use this to evaluate the rest of our query. There are equivalent ways to express a query with a with clause using a nested query. So this query has equivalent forms using the where clause and the from clause. The reason why you would want to use the with clause is because more complex queries might be harder to write if you didn't use the with clause. So here's the same query using the where clause and the same query using the from clause. If a subquery returns a single attribute, single tuple relation, that is a one-by-one table, that subquery is known as a scalar subquery. The value, or more accurately, the value extracted from this relation, we can use that as we can use that as part of an expression that expects a value. So this is the largest budget of all departments. This was evaluated from a query, and the output was a single column, single row table, where the lone value is the largest budget of all departments. This is another subquery where it's the average salary of all computer science instructors. So I am going to cut it short here because there is even a part 3 to this. So part 3 is all about how to update a database. I think I'm going to have to save that for a different time. But rest assured that this last part is also pretty short. It's all about section 9 of chapter 3, how to update a database. So I'm going to save that for another time. I'm going to leave off chapter 3 at this point, and I'll conclude chapter 3 at another time. Your next lab is going to involve a few more complex queries, ones that involve nested queries. So look forward to that one, okay? All right. If you have any questions, let me know, and we'll go from there, all right?